Okay, we're going to move to UCAR, and I'm going to introduce the speakers that you'll be seeing coming from there. We're very excited to have Fran Bagenal, who's a professor of astrophysical and planetary sciences at the University of Colorado, Boulder, and a co-investigator on the New Horizons mission. Her main area of expertise is the study of charged particles trapped in the planetary magnetic fields. Fran is interested in finding out if the solar wind interaction with Pluto's escaping atmosphere acts like a comet. Fran has participated in many of NASA's planetary exploration missions, including Voyager, Galileo, and now Juno. She chairs NASA's Outer Planet Assessment Group that provides input from the scientific community on the exploration of the outer solar system, including Europa, the one that everyone wants to go to. The other participant today at UCAR, we're very happy to have Vicky Hamilton. She's a planetary geologist at Southwest Research Institute in Boulder, and she's a co-investigator and the deputy instrument scientist on the Osiris Rex mission that you're now very familiar with, some of you. Her main interest is the mineralogy and history of planetary bodies, and her specialty is spectroscopy, understanding the spectral features of minerals and rocks in the visible, near-infrared, and thermal infrared areas of the electromagnetic spectrum, and using this knowledge then to identify the rocks and minerals on planetary surfaces. Most of her recent work has focused on analysis of data from NASA's many Mars missions, but now her focus is Osiris Rex. So we'll swing over to UCAR in Boulder.
Is that working? Can you hear us?
Hello?
Hello?
Okay. We hear you.
So do you want to fire away with questions, Sherry, or?
No, just go ahead and you guys can start your conversation.
Okay. So before we start going through the specifics of designing some missions, there are one or two things I want to go over about the New Horizons mission to Pluto, and comparing it somewhat with other missions to the asteroid, small objects of the middle outer solar system, right? The asteroid belt. So we've got up here, and I'm hoping that you can see this in other places, a slide that shows the Kuiper belt with the orbits of the giant planets, and then these red and white dots are all of the Kuiper belt objects. This actually is from the Smithsonian, Harvard Smithsonian website, and it's from yesterday. So they put them up as they get found, and you can see all these many, many objects. And we have to realize that the only one we knew about since 1930 is Pluto, and all these have been discovered since 1992. So beyond Pluto, the New Horizons go on to, we hope, another, if not two other objects. So this is something to keep in mind. The other thing I really wanted to show you, and I just put this together, is some of these variety of objects that we have in the Kuiper belt. And they're different colors, different shapes, different numbers of moons. They're all on the order of 1,000 kilometers or 1,000 miles. You can sort of see that range of the scale on the bottom left. And then I've put in here topical objects from the asteroid belt. We have Ceres. On the one inside the smaller one is to scale, and you can see that the largest asteroid is in fact a bit smaller than these large Kuiper belt objects, with the latest dawn picture on the right. And then Bennu, that you're going to hear a lot more about from Vicky, down here at the bottom left, very dark and relatively small. So to give a sense of scale, we can use thousands of kilometers, thousands of miles, and all this sort of stuff, but it's really quite useful to compare with Earth. And here we have Pluto and Pluto's large moon Charon to scale with the Earth, and this is quite useful to give a realistic sense of scale of what we're talking about. Just to show you, if you could just hold on. have a model. We're talking about models and constructing models, and I have a model here, which is quite useful. Actually, if you could, yeah, okay, right. Which, because these are locked in their orbits and spins, I hope you can see this, we've got a system where this is the balance point, which is outside the two systems. This is like a binary system, like a binary planet system. And you can make this quite easily out of pieces of polystyrene and stick like we have here. But what's a good thing to test your students to think about is, if you were a person sitting here on Pluto looking up at the moon Charon, what would you see and how would it change with time? Or conversely, if you're a person on the other side of Pluto looking up at Charon, what would you see or not see? So these are useful sort of conceptual challenges to your students to think about what you're seeing and moving in different frames and so on and so forth, and comparing it to the Earth-Moon system, which is very different. So that's just an example of something to think about. The important thing about Pluto and Charon is indeed, you've already discussed the fact that we don't have very good images. We don't really know what the surfaces are like. It's extremely cold. Whatever units you use, this is extremely cold. I was giving a talk in Canada, and they were very proud of their cold temperatures. And I said, you don't know nothing yet. The other thing is the color. Why has Pluto got these brownish colors? Big question. Very important scientific issue to discuss, whereas Charon seems to be more black and white. And again, this is important when we compare with other objects of the outer solar system. What makes them have different colors? And so why is Bennu so dark? Very important, big important. These are the big driving issues of solar system science. So we have these 6 objects that we are now going to study. Pluto and Charon here, and then these other ones, Hydra Styx, Kerberos and Nix, and we'll fly by. The X marks the spot of where we will be going through, we think, with New Horizons, we hope, and going through. You've already seen our friends, all of the eyes and ears of the spacecraft, different things that they will be looking at. We can talk more about that if you want. But the flyby is particularly interesting. We will be going by very quickly, going click, 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 taking pictures, sending them back as fast as we can. This whole close part is 2 hours. So 9.5 years to get there, 2 hours of close flyby. Of course, we will be getting good pictures several weeks beforehand and sending those out. But the very intense period is just a few hours. So that's all I have to show. Maybe you want to say a little bit about Bennu and
Yeah, so I won't say a whole lot because I think you've already heard about Osiris Rex today, and I'm happy to answer additional questions you may have or anything like that. But, oh, thank you very much. I have one visual aid, and it is this little object here. This is a 3D print of Bennu to the best of our ability to understand what it looks like. And this is based on radar data that were collected from Earth. And so Bennu is about 500 meters in diameter. So we were talking in the room here a little bit earlier about if you stood on the equator and you walked all the way around the equator of Bennu, it would probably only take you about 15 minutes, maybe a little less. It's that small. That's how tiny this object is. Actually, it would take you probably double that because we're talking circumference. But you know, it's a very, very small little object, and we know very little about it. We do know, I've got it painted this color for a reason, although this is probably a little too light. Bennu has a reflectance of about 4%. So that means all of the light that comes to Bennu from the sun, only 4% of that light gets reflected back to you as an observer. This object probably has a reflectance of about 15 or 16%. I'm just guessing, I haven't measured it. So Bennu would be much closer to looking like a charcoal brick than this. And there's actually a reason for that. We think that the sampling arm, which is that little blue guy sitting there, and then the sample canister, which goes into here. So the way this works is Bennu is sitting out in space, happily rotating, doing its little thing. And we're going to come in, and we're going to look at it using our science instruments. We're going to take a lot of pictures of it. We're going to use spectrometers to collect information about the composition of Bennu. And we're going to use all of that data to help us pick a place on Bennu where we want to collect our sample. Once we've identified that location, again, this is another process that involves both understanding the science of the surface of Bennu, but also the safety of going to that particular location we might want to go to, because we can't jeopardize the spacecraft. We have to be able to get a sample without harming the spacecraft or causing it to go into a safe mode or anything like that. So we go through a whole series of checklists and criteria for selecting a sample site. We do really low altitude reconnaissance passes to get the highest resolution data we can. We go through this whole planning process, and when we've gotten to the point at which we feel like we've got a site that is where we can go and reliably get a sample and do it safely, then the way we actually do this is that we extend the sampling arm, and because Bennu is rotating, we don't want to just come straight in at it. We actually need to match the rotation rate of Bennu. And while we're doing that, we also need to approach Bennu. So we need to be coming in towards its surface while precisely matching its rotation rate so that the relative motion between the spacecraft and Bennu is essentially zero. When we've done that, we come in, and the sampling process occurs very, very quickly. It's only a few seconds. We very gently approach the surface, touch it, and literally as we touch, canisters of gas fire, and those canisters of gas impart force onto the surface of Bennu. It, stirs up the materials that are sitting there on the surface, and there's a little tiny 2-centimeter diameter hole in the sampling head. And those canisters cause that material to go up into the sampling head. There's little flaps inside the sampling head so that the material doesn't fall back out. And as soon as that happens, within a few seconds, we immediately start backing away from the object. So we're not landing on the asteroid. We're not staying there. We're coming in. It's called tag SAM for a reason. It's touch and go sampler. So the idea is we come in, we touch it, boom, go the canisters, collect a sample, back away, and immediately go to a safe orbit away from the asteroid. So that's the basic process of how the sample gets collected. After we collect the sample, we want to verify that it's actually in there, that we actually got it. So one of the things that will happen is that the people flying the spacecraft will rotate the spacecraft around multiple axes, and they will actually detect the change in mass and balance of the spacecraft and back out how much material we actually collected. So it's going to be a really interesting thing to watch and see. So then if we have the sample that we wanted, this little arm kind of bends back in, and it puts the sample into the sample return capsule. This goes back. This is actually going to pop open and then close up again. And then at that point, we actually go into a period where we just kind of sit and wait for a period of several months, and then we come back to Earth. And at that point, we will be done with the primary part of the science mission at Bennu. We'll come back to Earth with the spacecraft. This canister will get ejected from the spacecraft and enter over the Utah test range. That's where we actually collect the sample from when we're done. The sample canister, if you're familiar with the heritage for that sample canister is actually from the Stardust and Genesis missions. So the canister, I think it's on the order of this size. I don't know the exact dimensions off the top of my head, but so it's about that size. So that's a small glimpse.
So I think the plan, right, was for Sherry to go through some questions that people might have.
Yes, we could go to the Applied Physics Lab first and see if there are 1 or 2 questions from our participants at the Applied Physics Lab. Okay, do we have some questions here?
I have a question. What about Bennu? What about Bennu? You want me to?
Yeah.
What were the characteristics of Bennu that made you believe that make you believe that there is a higher degree of organics there?
So one of the things that we do in just sort of general astronomical science and asteroid science is that we have the ability to use telescopic observations to collect spectral data of asteroids in the solar system. And we see that they have different spectral signatures. So at different wavelengths, they have different brightnesses or different thermal properties or that sort of thing. And so we've classified asteroids into different groups. That in and of itself isn't enough to tell us what Bennu is made out of. What we actually have to do is then relate that information to materials that we know about here on Earth and their spectral properties. One of the best analogs, though, is going to be meteorites, because we know that asteroids are the parent bodies of meteorites. So Bennu in particular is a type of an asteroid called a B-type, and that just means its spectrum looks a certain way. And we have found that there are meteorites in our collections that have similar spectral properties. So those properties are what lead us to infer that Bennu is rich in these organic materials and certain other kinds of minerals. That's how we do that.
One more question from APL.
In what part of the asteroid belt is Bennu?
So Bennu is actually an Earth-crossing asteroid. It is in it's a near-Earth asteroid. Part of the last S in Osiris is for security, and we touched on this maybe in one of the earlier presentations, that Bennu is actually an asteroid because its orbit crosses that of the Earth. It's a potentially hazardous asteroid, and it's actually got some, I don't know what the exact numbers are today, but it's got like a 1 in 1,700 chance of actually impacting the Earth about 170 years from now. So it's in an Earth crossing orbit rather than being out further in the main belt.
Okay, let's move down to the Johnson Space Center in Houston for a couple of questions.
Yes, we definitely have a couple of questions. We'll start with our first question.
As far as the recovery of the sample craft goes, are they still going to try and pluck it out of the air with helicopters like they did with Genesis and Stardust, or are they going to try and go with something a little simpler?
No, the current plan is that the capsule will land in the Utah test range, and we have a whole team of scientists on the team who will be there waiting for it, and they'll be tracking it as it enters the atmosphere, and they will run out and retrieve it as soon as they possibly can locate it and get to it.
We have a second question.
As far as the actual sample capture, is it a one-time shot, or are you going to have enough gas in the canisters to go for a second attempt if you don't get enough material that you want?
That's a really good question. So there's two different cases that you've described. One is, do we get enough sample? And so in that case, I'm not sure that the science team has actually come to a conclusion yet on what we would do. We will, I described the maneuvers they'll do with the spacecraft to try to understand how much sample we've gotten. If it looks like there is sample in there, it's detectable that they know we've gotten sample. Odds are pretty good that we won't go back for more. At that point, we're just risking the spacecraft, we're risking the sample, and we don't want to do that. If, however, those measurements make it show that it's unclear if we got a sample at all, then we do have a decision to make about whether or not we want to go back and try again. And we do have the capability to go back and do a second touch-and-go maneuver if we need to.
Okay, JPL, we've got a microphone right here. If you've got a question, please go ask.
Good morning. I have a question. This is maybe a little bit out of the Osiris Rex mission, but NASA announced last year they're going to try for a mission to actually send a robotic probe out to capture a very small asteroid, bring it back into moon orbit, and then a manned mission to sample it from there. How would Osiris be different from that mission? Or maybe a better question would be, how would those two different missions work together?
there's not really a direct linkage between the two missions, but I think what can happen is that the Osiris Rex mission can help engineers understand how to operate a small spacecraft in the vicinity of a very small object that doesn't have a lot of gravity. Most of the space missions that we do with NASA's planetary science missions are missions like New Horizons, where you are flying past an object and making measurements, or you very commonly will go into orbit around an object, like if you're at Mars or even at Jupiter, or any number of places. You're in these very stable engineering environments. Osiris Rex is very different from those because it doesn't go into an orbit. The Bennu isn't big enough to have enough gravity for you to get into an orbit around it. You can simulate being in orbit, but you're the one doing the work. So what Osiris Rex helps us understand is how to operate a spacecraft in a very low gravity environment around an object, how to position yourself, things like the solar wind actually apply enough pressure to our spacecraft that we have to correct for that very actively on a regular basis. Those are kinds of activities that this asteroid retrieval mission will have. Those are the kinds of things they'll have to do too. Beyond that, what my notional understanding of the ARM mission or the asteroid retrieval mission is that, beyond that, the things they want to do deviate pretty significantly from what we're going to be doing. So I'm not, that's probably a point of departure for those two missions.
Thank you. Thank you.
Another question at JPL?
I just want to know, how difficult is it to actually get the orbit to be the same going around it, and if they are off, what would happen if they're just like off by an inch, or not going fast enough or going too slow?
Okay, so that's a really good question. Well, to me, I'm a scientist, not an engineer, so it seems really, really, really hard. But the engineers say they can do it. They are working very hard to try to understand what is the kind of positioning and positioning accuracy that they need to have in order to make this work. I'll tell you what we're doing to help us with that before I tell you what would happen if we didn't do it right. We actually have what we call tag rehearsals. So again, tag is touch and go. So that's the actual sampling procedure. And we have literal rehearsals for this process that are scheduled into the mission, where we will, be out in what we call our safe home orbit, where we're just kind of station keeping around the asteroid. But we will have these rehearsals where we come in closer and closer, and we have things that we call match point, where we think now, okay, we're, some distance still away from the asteroid, but we've matched its rotation rate. And then we will do that for a little while and continue to make sure that we're actually keeping that rate matched. And then we go to the next point where we get a little bit closer, and we, sort of pause at that point, and that's called a checkpoint. And we're a little bit closer still. And we'll do that once, and then we'll back away. And we'll kind of look at the data we get and check how well we did. What do we need to do differently? Do we understand what we need to understand? Did something unexpected happen? And we have 2 of those rehearsals before we actually try to do the touch and go sample activity. So that will help us gain a lot of the information that we need to plan that activity very precisely. If it weren't to go right, if we were not to accurately match speed with the asteroid, basically what you can imagine is that our sampler head would drag along the surface, and that could damage the sampling head. It could rotate it in such a way that the gas jets don't allow us to disturb the regolith in the way it's intended to in order to get the sample into the sample head. And in the worst possible case, you could drag that arm along the surface and potentially cause the spacecraft to impact the surface if again, there's very little, there's no gravity, there's no atmosphere, little tiny forces on that spacecraft could cause it to swing around very wildly. So this is something, we work on very, very carefully and really want to make sure we get right.
We have one more question here.
Yes. Hi, thank you. My question is, why? So besides the obvious of what we intend to find out from the sample, are there any questions on exactly what we want to find out after gaining the sample and doing all the analysis?
So the Osiris part of Osiris Rex has several different components to it. The O in Osiris Rex is origins, and that refers very specifically to the fact that we've targeted an asteroid that has what we believe to be among the most primitive material from our solar system's formation. And so one of the things, I said before that we know that there's a relationship between asteroids and meteorites. We can do a lot with meteorites, but most of them they've all had to transit the Earth's atmosphere. Some of them have sat on the surface of the Earth for a very long time. They get water, they get contaminated in many kinds of ways. They're not pristine samples. So even though we can learn a lot about the origins of the solar system from these meteorites and others, there's still no pristine samples in our collections. And so that's one of the science objectives of collecting this sample, and why we want to do this, is that we want to go to the source, get that sample, keep it pristine until we can open it up in a laboratory in a very controlled environment where it won't get contaminated. So that's one of the things we want to do. The next letters in Osiris Rex are the spectral interpretation. That is helping us to understand, okay, we went to this asteroid thinking it would be representative of a certain class of meteorites. Is it? If it's not, what do we learn from that about our ability to interpret the compositions of other bodies in our solar system, and all the inferences then that we make about the processes in our solar system based on that information. And then the next few letters, the RI is the resource identification. People are interested in, again, there was a reference to this asteroid retrieval mission. One of the things people are thinking about is, the ability to use these objects in our solar system as a source of things like precious metals. And so that kind of falls out of the what does a pristine sample of one of these bodies look like? And then the S in Osiris, the last S in Osiris, is the security element, that, as we talked about, this is a potentially hazardous asteroid. We want to go, one of the things that we're going to do is not just collect the sample, but actually understand in great detail the forces that operate on this asteroid and cause its orbit around the sun to change with time. And in fact, Bennu probably started out much further out in the solar system than it is today. And as it rotates, the sun heats up the day side of the planet. And as that day side goes to night, the emission of that heat energy back out at night actually imparts a force that causes the orbit to change over time and come in closer to the sun. That is a force that we understand pretty well. But by going to Osiris, or taking Osiris to Bennu and making measurements in situ at the asteroid, we'll be able to understand those forces and how they work much, much better. And that will help us understand how asteroid orbits change over time and the dangers that these asteroids that come into Earth-crossing orbits might pose. So I hope that addresses some of those questions.
Wonderful. This is Whitney. I'm standing in for Sherry. So I had a question for you, Fran. I know that you were one of the leads in developing the student dust collector, and actually it seemed like kind of a perfect comparison between your two missions right now, because in some ways you're extremely different missions, and in some ways you still have some shared objectives, and I thought that perhaps your student dust collector as an exemplar of that would be great for people to know about.
Yes, let me just pick up the model and I can demonstrate this a little bit. So the student dust counter, named by Venetia Burney, the young girl who named Pluto back in 1930. If you hold it, that'd be great. Here on the opposite side to the antenna, we have a little square. It's about the size of a laptop that has a bunch of little pieces of plastic. And as the spacecraft, which is moving, if we imagine the sun and the Earth are over there in that direction, and we have the antenna communicating with them, as it moves through the solar system on its way all the way out to Pluto, 33 astronomical units away, it collects pieces of dust that it goes through. The way this works is you have a piece of plastic, and as the dust hits it, it's special plastic in that it generates a voltage across it when it receives an impact from a dust. And so we measure those and send those signals back using the antenna to Earth. And so we've been detecting about 1 or 2 dust hits per week. Now, that's not a lot of dust. There isn't a lot out there. Space really is pretty empty. But there is some dust that's generated. Now, the forces that you were talking about to do with heating from one side and radiating from the other side, and the solar wind, which is very, very tenuous, but enough over a long period of time to clear out the dust, or for the dust to move inwards in the same way that the Bennu has moved inwards. We think that the dust in the outer solar system comes from the grinding up or the bashing into each other of these Kuiper Belt objects over millions of years, generating some dust, which then slowly moves inwards. And so we've been able to measure this now since over the 9.5 years of the time it's taken New Horizons to get out there. And the students have been there measuring the dust and taking the data that's coming down, posting it on the website, writing 2 PhD theses about modeling how this works along the way. So indeed, there are a lot of similarities in terms of trying to understand origins of the solar system and evolution of the solar system. How do these orbits change? How do you grind down material? How do you use, if you have impacts, sending out dust and so on, and measuring that stuff in the outer solar system? Yeah. Right, so we're talking about models here, and it's probably worth just talking a little bit about these models, because this exercise that we've been doing here has been to compare different models. Oh, thank you so much. So we have a variety of different models that we can use, and here's a paper one that we can make by printing it out and putting it together with glue. But in reality, what we use when we're designing missions and we're trying to work out what's going on, we often just do this. We take a coffee cup, we put some axes on it with pens, or these are stirrers. We put arrows. Now we might make this as the camera here sticking out, and we go through this exercise. If you would just hold this for a second. If my fist is the object, Bennu or Pluto or any object that you want to do, we take our spacecraft and we fly it by and we say, okay, we want our cameras taking pictures like this. Oh, but wait a minute, we have other instruments that should be measuring the solar wind, and they need to keep that way. So let's find a design of an orientation that allows us to do what we need to do, right? And so I've done this when designing missions. We do this all the time because we don't have enough fingers to make it work with our hands. Or we may get a little bit more sophisticated and do a paper one. And X, Y, Z, these are the RTGs, and this is the antenna. We do the same exercise. Now, if we get to be really wealthy, we go and get a 3D printer to make one. And this is the first time I've actually picked this one up because it's pretty fancy and it's just been made. And yeah, you can do the expensive one to do the same exercise. But to be honest with you, this is just as good. Okay. But we use these models. This isn't just a school exercise. We use them to design our mission and decide what we want to do to make these missions work and operate them. This is my pocket version for New Horizons with axes that Will Grundy, one of the co-Is, put together because he was so frustrated trying to work out where the cameras would be pointing at different times.
So I have a question that I get asked a lot on your behalf, which is why a flyby? If you've gone for 9.5 years to Pluto, why the heck aren't you hanging around for a little while? And I think a lot of people, that's something they wonder.
Indeed, that's a very common question I get. And the answer is that Pluto is relatively small. It does not have a lot of gravity, and so it's hard to get into orbit around an object with a low gravity. It's also hard to get into a large orbit around a large object like Jupiter. You need to have thrusters that will slow down the spacecraft so it gets captured into orbit. And when you're designing a mission, you have to decide, what am I going to put on my spacecraft? How many instruments am I going to put on? How are we going to deal with the three big issues, right? We have propulsion, we have power, we have communication. Those are the three biggies of space missions. And so you have to decide, am I going to put all this extra propulsion onto the spacecraft so I can slow down and stop when I get there? Or am I going to put my resources, and the biggest resource in all of space exploration is mass, because you have to have a big rocket that is going to send it out from the Earth and get it out on its trajectory to the objective? Or am I going to put all my energy into fuel? Or am I going to have instruments on board that will take data? And am I going to have an antenna that will send a lot of data back? And so you have to balance those resources to find an optimum. And what we found over the years is that when you go to the first place, you just need to take a few kinds of data, different kinds of data, and send them back. So we've nearly always, the first missions have been flybys. So we've done flybys of asteroids, flybys of planets, and flybys of distant planets like Pluto. And so you go from a flyby, then you go into an orbiter, you go and get a detail, you focus down, and you say, okay, now I want to stay there, make measurements over a period of time. And then finally, if you have the resources and the time and the energy and so on and so forth, money, you will then go in and land. Or you'll do what Osiris Rex is, what we call scratch and sniff. You can call it you call it touch and go, but it's basically scratch and sniff, right? And we could think of targets where we want to do that sort of thing. So you build up your level of sophistication once your knowledge is increased and your questions, your science questions, become more and more focused. This is what I really need to do. I really need to touch the surface. Or you may do, like we do with Europa, we want to know what the surface is like, but we can't land on Europa right now because we don't know the geology well enough. We have no idea where to land. It's too rugged in some place. We don't know where it's smooth. So we have to do the next mission, which would be a flyby mission, do multiple flybys close up of Europa to get a sense of the geology, so then we would know where to land. So it's all part of the process of evolution of missions and so with Pluto, it's the first time. Just getting a picture is going to be so cool. Let's do that first.
Awesome. So another question, I think, is that for many of our students, they feel like that, there's the old, it doesn't take rocket science, or that's rocket science. They don't feel like sometimes this really sophisticated science and engineering is for them. So I was wondering for each of you what you think the characteristics are that you would want your, younger learners to feel like they could bring to the table in terms of imagining and starting to apply their growing knowledge to a potential career, or just even awareness of astronomy and space science and the great things that we're learning out there.
I will say very quickly, I think there are two important things. One is curiosity. What's out there? I want to go find out. And the other is persistence. Just sticking with it. Yes, the math homework is hard, but you got to stick with it. Stick with the math homework, stick with the physics, stick with asking questions and trying to find the answers. And you'll get there. Persistence is the most important, I see in the students. Not necessarily the brilliant ideas, but, they don't follow through.
I think those are really excellent points, and agree with both of them. To add to that, I would say that there's a whole lot of ways in which you can get involved with spaceflight missions. It doesn't have to be as a physicist or a scientist or an engineer. Although those are great careers, a lot of kids, especially younger, may not know what they are or understand what's involved with them. I think trying to find the angle where, just encouraging kids, figure out what it is you enjoy doing. Are you really detail-oriented? Do you like making things and building things with your hands? Maybe, that's more of an engineering kind of pathway. But the how does it work, just, wanting to know what is it that you want to know how it works. Is it that you want to know how the spacecraft operates, or is it that you want to know what the asteroid is made out of? And so kind of trying to figure out what is the thing that's most interesting about this to a student is kind of maybe where you can get some clues as to where to guide them as far as their interests go. But, somebody mentioned earlier that, artists and renderings and the ability to take spacecraft data and manipulate them in a computer so that you can take a flat picture and overlay it on a three-dimensional model so that a scientist can visualize that. We have a ton of software engineers who are involved with our missions to do these kinds of tasks. So if you're into computers and computer programming and visualization, there's tons of pathways to go there that get people involved directly with the mission and have a key role with the mission. For me personally, I didn't think I was going to be a scientist until I was in college, and so I ended up kind of changing gears very late. For me, it was geology. It was realizing I could see geology around me all over the place, and so I started wondering about the geology of other places and got involved with it that way. So I'm not sure if that's a very direct answer, but maybe it helps. I don't know.
Those are both awesome answers. And we want to thank you for your conviviality. You're just friendly, lovely, helping us get the big picture here. I know that, I'll be taking pieces back from your contributions to the stories that I share with kids in the future. So thank you so much.